Okay, so welcome to the final part of the lecture series, and we're going to be talking about maths mechanics for the next two lectures. And then we'll have a revision lecture where you can ask any questions that you might want to might have about the whole module. So we're going to start actually by talking about gravity or the center of gravity. So when you think of gravity, you might think of Sir Isaac Newton at his house in North Yorkshire, where an apple dropped upon his head. And if we think about the apple dropping upon his head, this is our apple, this apple has its own center of gravity, and the center of gravity is the point inside of it. So likewise, if we were to have a bar, a long bar, or a piece of wood, or whatever we want to have, or a piece of string which was straight, what we could say is, well, actually, this bar is made up of lots of little sections, each with their own center of gravity. Therefore, if we were to split this bar up into many, many, many sections, we would see that all of these sections each had their own center of gravity. They're just connected to one another. But what we could totally say or globally say is actually, well, because all these points are just little points, well, they're all going to act about one point. And because this is an equal bar, perhaps it was suspended at both points here, we would know that the center of gravity would have to enter or would have to act around the center point itself, because that makes sense, because that's the average of both sides and would have this gravity which is pulling it from the center. Okay, so let's think of this in a bit more. That was a kind of a simple example. But what happens if we have some weights? So say we have a bar like this, and we want to find its center of gravity. But we actually have a couple of weights on it. So we have maybe a point here, which is, we'll call this P, and we'll call this Q, as I have in the notes. We can say that this is point A, we have point B, that's probably a bit further up, isn't it? Point B, and we have point C. B is not very good. Anyway, so what we can say is we've got some distances here. So I'm going to draw those 2 meters. We've got some weights even, which are 4. This is 4 newtons, 2 newtons, and 3 newtons. I'm just going to get rid of that line there. Okay, and then we've got some distances. So we're going to actually want to find the center of gravity. And this isn't equal now, so we're going to have 2 separate distances. So the center of gravity is going to be either on one or 2 sides. So we're either going to find it from P or we're going to find it from Q. So how do we do this? Let's find out the distances, which we've written here. So we know this point is 2 meters or 2 units away from P. It's also from these two are 3 units away from A and B, and we have just 1 unit here. It's not to scale at all. So what we're trying to do is we're trying to work out what the average of all these are. So we need to work out maybe the average distance and the average weight. So how do we do this? Well, we have to talk about moments now. So what are moments? So you think if you're on a seesaw and you had a distance from maybe there was a light person of weight 4 and they were sat at 2 meters away from the pivot from P, then obviously they were going to have less effect than someone who's placed 6 meters away at point C, even though they're lighter, because of the moment or the leverage effect. You'll have found this out before, maybe when you've used a spanner or when you've sat on a seesaw. The further away that you pull something, you're going to get a stronger force. So what we can say here is actually, well, we could multiply these together and say, well, about P, so we use this little arrow, we can say, well, our force of maybe 2 units times by 4 units, 2 times 4, is, and then we have to add the next one. So we have 2 plus 3 is 5 times by 2, which is 5 times by 2, plus 2 plus 3 plus 1, so that's plus 6 times by 3. So if you can think this distance, this moment is created by the weight multiplied by the distance, is equal to well, how are we going to balance this out? Well, we want to find the average distance. So the average distance, so we're going to call that just x bar. And then we want to find out the average distance with all these forces acting on them. So that would be the same as saying 4 plus 2 plus 3. So what we have now is we have a way of finding the solution for the moment about P. So we could say that that is 8 plus 10 plus 18 equals x bar, which is multiplied by 4 plus 2 plus 3, which is 4 plus 2 plus 3 is 7. That's 9. And if we just stick that into our calculator, what we'll actually find is it's possible for us to calculate. The moment, and we'll find that x bar is equal to 4. So we know that our distance, where the center of gravity acts around P, is at 4 meters. So we couldn't actually work that out from Q because we're missing this information, but that's okay. So what have we actually done here is we've actually created some sort of equation, and the equation we've sorted is we're saying that our total of our weights multiplied by our distance is equal to our average distance multiplied by our total number of weights. So all we're doing effectively is we're finding the average or the mean location of where the centroid or the center of the forces are acting. So if you think of this, this is just a more complex way of working out ratios. And if you were to sit and work this out with maybe a piece of string and a set of beads, you could work it out just by eye. So, okay, so that's center of gravity. Well, I've not mentioned mass, and maybe you've heard of center of mass instead of center of gravity. Well, I was just talking about weight here. So we actually have this force gravity, which is continuously acting upon us. And we know that weight is a function of newtons, but our mass is something different. Our mass is something which is controlled by the Earth's gravitational constant. So gravity on Earth is equal to 9.81 meters per second squared. And if we'd had chance, and in this module, there's a way in which we can actually physically derive this with balls and gates, but we don't. It's not possible for us to do the experiment. Perhaps this will be an experiment, you'll see another time. So what we can actually say that our weight is equal to the mass of something times by the gravity. So this is just our gravitational constant of 9.81. So for example, if we're on the moon, our gravitational constant is of about 8. That would mean we would weigh less on the moon, but our mass would be exactly the same. So how does this affect our equation that we've just looked at? So I've just said that our equation is our total weight multiplied by our distance n is equal to x multiplied by our total weight again. Okay, so what we see here is actually, well, if we substitute our mass and our gravity in, we can say that W equals mass times gravity equals mass times gravity, so that would be mg multiplied mn multiplied by g multiplied by xn, so that's the sum of all these, is equal to x sum mng. So actually, this doesn't really matter because this gravity is just a constant. So effectively, in this case, when we're trying to find the location of the center of mass or the center of gravity, it doesn't really matter which way we're doing this, if we're using weight or we're using mass or we're using gravity. So, okay, so we'll now move on. On the next part, we're going to have a look at how this applies in 2D shapes. So we'll begin that in a